and the field phi, substitute by phi dash I, phi dash A equals phi A plus variation of phi A. And then you introduce a substantial variation. As in other subjects, which we also did literature courses, tensors, spinors, and relativistic spinors, tensors and relativistic wave equations, tensors and relativistic wave equations, relativistic wave equations. It's with Lecky in Edinburgh, 1953. So the substantial variation, there you can find details to that substantial variation. Delta star, I mean, we just subtract a transport term from the variation of the phi. So variation of phi A minus the transport term is variation dx k partial k of phi A. Okay, and then I vary my coordinates and my fields, and I substitute it in the action function, and what I find is the variation of the action function dI equals d for x, and now a bracket, and here I get what is called the variational derivative, dl over d phi a times the substantial variation, delta star of phi a plus, and I get a surface term. We have heard in Jim Lister's lecture on his conference last week in Taiwan, he used this surface term for making energy quasi-local in gravitational theory, so it's the same type of surface term. So it's L times the variation of x plus partial derivative of L with respect to the velocities, that is partial, parenthesis, partial I, phi a times substantial variation of parenthesis closed, bracket closed. So this is what we get. And this variational derivative, most of you would know, but let me nevertheless define it in order to tell you exactly what I mean by this. This is partial L over partial phi a minus the divergence of parentheses, and here I have the partial derivative with respect to the velocities, partial dI. This is a variation derivative, and if the surface term doesn't play a role, if I make the variational principle in the prescribed way, basically Hamilton's principle, then dI has as a consequence, equals 0, has as a consequence that we have the field equation, the Euler-Lagrange equation, dL over d phi a is equal to 0. This Euler-Lagrange. Okay, but now let me come to the conserved quantities, which we are interested in because we studied, of course, the Poincaré group. translations and rotation, and what we now want to have is a conserved energy momentum, and angular momentum currents. And angular momentum currents. I prefer here the name current, because this is exactly what they are. We have in nature, for instance, the electric current, we have the weak current, we have the strong, the isotopic current. Well, and energy momentum is also flowing, it is a current, and so is angular momentum. So they are quantities of the same type. What in electricity is called the electric current is here the current of energy momentum and the current of angular momentum. It's in the development of elementary particle physics, so-called current algebra played a big role. Particle physicists amongst you would know that. And this was one study, commutation relations of currents, because one didn't know the underlying theory and tried to test the matrix elements which were determined by these currents. And what we first get is a Noether theorem, Noether theorem, I think that was 1980, 70, I don't know exactly. It was shortly after GR was discovered, and it was a theorem which was largely forgotten, and only the quantum field theoretician Bogolyubov-Shirikov discovered it again. And there is now, we talked about it in Taiwan, a very nice book by a French physicist, historian, half and half, or mathematician,
Schwarzbach,
who's, I think with an E, Schwarzbach.
It used to be Yvette Kosman.
Sorry?
It used to be Yvette Kosman.
Kosman. Without the E?
I'm not sure about the E.
Okay.
But she married Schwarzbach.
Schwarzbach, yes. Okay. Yes, but the book is, it just called something like the Noether theorem, and it is a translation from the French, and the English translation is annotated and improved appreciably, I was told by people who know the French edition. And it's Springer, I think. Springer. About 2010.
So finally we can now read Noether theorem in English.
Yes.
Well, actually we could do this a little bit earlier, but not much.
Yes. Okay.
Razel, do you want to take a 10-minute break?
I'll take a break.
Can I finish the
Sure.
conservation laws? Then that will fit nicely. Yes, great. So I recommend this book for people who are a bit interested how such things develop. And I mean, this is one also in quantum field theory, one of the fundamental theorems in every theory, Conserved quantities is, after all, most of the things we know about nature is via conserved quantities. I mean, a lot at least. Because that brings symmetry into the world, or perhaps the symmetry was already in the world, but with the help of these theorems we can discover these symmetries. Okay, so you can see it right away. If you now, I just show it for the translations of the rotations, I leave it to you. So if you have now a rigid translation, so everywhere the same, and this is of course possible in a Minkowski space. It's not possible in a Riemann space, but here it's possible. A rigid translation. What is it? Well, dxi is just a constant. Dxi is equal epsilon I. And the fields don't transform. P, phi, A are equal to 0. And you can go into, you can now substitute that. You see the dx, I'm missing. Here the dxi just becomes the epsilon I, and here you have the substantial variation, and this substantial variation, the dxi then has a constant, so you have here x epsilon k times the gradient, and this vanishes because phi is not so complete. And so you have here a gradient, and you have here just a conical. I mean, you have the epsilon times this, and then you can take the epsilon in front of the integral, and the whole integral looks then at the change of the action is epsilon k times d for x, partial derivative with respect to I, and here you have just L delta ki minus dl over d di by a partial k of phi a. And this is equal to 0, and then that's valid for all domains, etc., etc. So this has to be equal to 0. And this, in the parentheses, is called the canonical energy momentum tensor. The canonical, the word just means the right one, or the one which one should believe in. I mean, partly it's a word which is used in the church, in Catholic Church, but this canonical is always the right thing. So we have the right thing here, so we have here the canonical stuff, the blackboard. So the canonical energy momentum tensor, it's of Latin origin. Canon means something like room. T ki is by definition just what we have here under the parenthesis, L times delta ki, the Kronecker symbol, minus partial dl over partial I phi a times partial k phi I. This student should know by heart this canonical energy momentum tensor, because a big part of physics is ruled by this tensor, and the Noether theorem is then just that the rigid translation leads to the conservation of this tensor. This is a Noether theorem, and this shows us the fundamental. We can now then look at the different components of the energy momentum tensor, and then we recognize that one component is the energy density, three other components is the energy flux density, and then there are components, the momentum density and the momentum flux density. So you have, and they are all together for 16 columns. So it's not symmetric or anything, it's arbitrary symmetry. So this is the energy momentum tensor. Should we make the break now, or should we get the rotation done in 2 minutes?
Okay, 2 minutes.
Okay, you stop me, you know. Because this concludes it in a nice way, hopefully nice way. So we have rigid rotations. Of course, Lorentz rotation, I should say, not so the SO13 is at work. And now what we have to do is to think how the field phi changes under Lorentz transformation. If we have a vector field, we know how it changes. If we have a scalar field, it doesn't change at all. If we have a spinor field, there are certain rules. So we have to invest the knowledge of how this behaves under under Lorentz transformation. If we do that, and we have this rigid translation, and we do the same stuff as we did here, we determine the dxi for the rotations, then we find the following. We define the canonical spin angular momentum tensor. Spin angular momentum. There are orbital angular momenta and spin angular momentum current. And this is then just coming from this piece. Here you have then the behavior under Lorentz transformation. S tensor, the canonical tensor is called SKLI. I'll just take the indices which I used in the derivation. It's by definition DL over D I P A. And now here we have the generators who generate the Lorentz transformation of the field KL in brackets, which means anti-symmetrization, BA, placeholders, and here we have the field B, sum over B. No, maybe A, yeah, we have. No, this is not B. A. Okay, and this is anti-symmetric because this is because there are rotations, so that's minus S L K I. One exercise for students, I was asked by a student that is to derive the neutral theorem, this theorem, by the same procedure how I did it for translations. He just has to substitute what the rotations are, the dx, bx, and the rotations. And then we find that the divergence of this tensor is not conserved. So spin is not a conserved quantity, even if you find this sometimes in books on nuclear physics, I saw such things. But you have to add the orbital angular momentum, which is, I write it in longhand, 1/2 of xk times t l I minus 1/2 x l t ki, spin orbital angular momentum, and now since I have only experienced people here in the audience, I can take an anti-symmetric bracket, which is 1/2 of this minus commuting of 2 indices. I can leave off that and feel the 1/2. Okay, and now I can differentiate this, of course, and then this, and differentiation of x gives me just a Kronecker delta. And differentiation of the t is 0 because of the angular, because of energy momentum conservation. So I can rewrite this law in a way that can be easily generalized to curved and tauthy space-times, which would not be possible with this, because x is not a vector. This is a coordinate and cannot be generalized to curvilinear systems. Is it plus or minus? I think it's minus. But I don't bet my life for that. KL anti-symmetric is equal to 0. So this is the Noether law for rotations. And if you have no spin in your situation, then the energy momentum tensor is symmetric. But if you have spin, then it's not symmetric, and there is nothing wrong about an asymmetric energy momentum tensor. Some people think there is nothing but a symmetric energy momentum tensor, all the others are artifacts. Okay, and so that is where you can now take a break of, what did you say, 7 minutes?
Yeah.
Okay.
10 minutes?
10 minutes, okay. Thank you for your